Alright, welcome back. My name is Anshu and this is my channel Bottleneck. This is a data structures and algorithms series. In this series, we are going to learn and implement data structures and algorithms using Scala functional programming approach. In our previous video, we had implemented a directed graph and we implemented a breadth first search algorithm. Breadth first search is a traversal technique like we had discussed earlier. There are few things which I would like to highlight currently. Let's see how the breadth first search traversal worked. So if you had missed my previous video, I will post the link in the description. So just a recap. So first it went to 2, then it went to the next level and it traversed 2 and 1, then it went to 3 and then 4, 5 and 4. Why it was traversing right and then left first? The reason is the value here it is prepended every time whenever a new node is added. This way if we are doing it, it's not optimal. The reason is whenever you prepend anything to list, the head is reset. Resetting head for a long list is expensive operation. So let's append this value to the list rather than prepending. So how it will look like now? As we are prepending the value, this is going to change. So how it will look like is 0, then it will go to 1, then it will go to 2, then it will go to 3, then it will go to 4, then it will go to 5. Similarly, it's going to change with the DFS as well. So it's going to 0 first, then it will go to 1, then it will go to 3, then it will go to 4, then 5, and then it will come back to 2. So the only difference between DFS and BFS implementation is we are backtracking in both cases, but here we are trying to implicate the logic of queue. Here we will be using simple stack. So time complexity will remain same. There is no change in the time complexity where V is the vertices and E is the number of nodes. In the worst case scenario, DFS visits all the vertices and edges once. Now, in terms of space complexity, even there isn't much change because it is going to use the same space as before, but the implementation or the way it is little different and it is faster because it is using stack, which is just push and pop. Here it is in queue and dequeue. Now let's first run this application to see that whatever change we did is as expected. Alright, so the result is 0, 1, 2, 3, 4, 5. Let's validate it once. So we are going to 0 first, then the second level 1 and 2, then it goes to third level, then the final level 4 and 5. 0, 1, 2, 3, 4 and 5. Perfect. So this is how it is going to look like for BFS. Now let's implement a solution for depth first search. Alright, let's write a method private depth DFS. Alright, it's going to be type of V. The input will be first as usual graph. Let's write the graph. Okay, so it's going to be graph of type graph and it will be of type V, graph of type V. Then there is going to be a start element which is again type of V. It is going to return a sequence of values which is basically depth first search traversal. Now let's implement a helper method. So it's going to be DFS helper. So what this helper is going to take, same as before, it is going to take a value as a sequence which we will name as stack. Oh, sorry. Alright, which will be type of V. Again, we have something called visited to track whatever we have visited. This is going to be set of V. Now let's give it an initial value, set of V as empty. Third value is the accumulator, which is basically a sequence, that is our traversal. So it is going to be sequence of V. The initial value is going to be nil because it starts with nothing. Now it is going to return a sequence of V. Alright, let's implement the DFS. Let me minimize this window. Okay. Now as before, we will implement a pattern match on stack. Okay. First case is I don't have anything, it's done, so it's going to return accumulator. So now we have the DFS ready. Next case, it's going to be head and it's going to be a tail. There are some value in the stack. Now as before, we will compare if visited contains the head. Alright, so if it has the head, nothing is going to change. So DFS helper is going to return with tail, comma visited, comma ACC. Alright, but what if, okay, the next case, else. In this, we will get the neighbors. Alright, so this neighbor is going to be graph, and we call the neighbor function from there, neighbor method with the head. Now we have to filter whatever is visited. So let's do filter not. I don't want anything which is visited. So visited contains. Alright, so what we see here is a syntactic sugar from Scala. So this will help us to filter out any sequence for a sequence where the value is matching what is there in visited. So it will occur for each and every element of the visited. Now let's watch closely. We are going to call the DFS helper. So what we are going to do is we are going to add both the sequence, and we are going to call the visited plus head. It is amended to head. Now we are just again appending head to the accumulator. Alright, so the difference is here, if you notice, in line number 81, neighbors plus plus tail, and here it is tail plus plus neighbor. So this is where the basic difference is. Rest of them is going to remain same. We are just trying to replicate the logic of stack, where this, just by adding this, we are keeping our neighbors first, that is going to be accessed. Here we are implicating the logic of queue by just appending or the adding neighbor to the tail so that it will be processed later. Okay, now we have to call this helper method. Let's call this helper method DFS helper. So it is going to be sequence of start. Alright, so now this is implemented. Let's test this. So let's print ln DFS and let's give the value as G as in graph. Alright, something is missing. We have to call this DFS outside the DFS helper. Alright, so this is our DFS helper. Let's call it here. Okay, now we pass the first value as graph and the next value as 0, which is the starting point. Let's print this and fingers crossed. So we are expecting something like this. So what we are expecting, it will go to 0, then 1, then it will further go down to 3, and then further go down to 4. There is nothing. Then it will backtrack to 3. 3 is already done, so it will go to 5. Then there is nothing. Again it will backtrack to 2, and then finally it will backtrack to 0. So whatever is already present, it is not going to add, but anything which is not present in visited will be appended. Let's run this. Alright, so this is our BFS and this is our DFS. Let's validate. So it goes to 0, then it goes to 1, then it goes to 3, then it goes to 4. Now backtracking happens. 3 is already there, it will not add it. So 5, now 5 is appended. Again it goes back to 3. So 3 is already visited, there is nothing. So then it goes to 2 and 2 is appended, then it goes to 0. So now in this method, one important thing is there could be a cyclic order in the graph, which is very well taken care. So due to this cyclic order, we can see the nature of queue here and the nature of stack here and the nature of queue in this BFS. So normally we because being it's using stack, so normally in any other algorithm which uses like topological sort, we are using DFS to sort the data. Okay, so this completes the implementation of DFS and BFS. And if you enjoyed this video, please like and subscribe, and see you around in the next video. Thank you.